Hello world, Joshua here at JTC Education, and today we're going to be looking at the infamous mole. Nope, not this guy here. This guy up here. Chemistry's standard unit of amount. Indeed, the mole has eluded chemistry students for years and years and years. And yet it's fundamental in stoichiometry, quantitative chemistry, chemistry of numbers. So, let's get these sneaky moles back in check. So the first question we should ask ourselves is, what is a mole? And if you were paying attention in the introduction, I already explained that 1 mole is the standard unit of amount in chemistry. And that is exactly what it is. 1 mole is nothing more special than 6.02 times 10 to the 23 things. And those things could be anything. Okay, I've got a silly example here for us. What is 1 mole of pennies? Well, 1 mole of pennies is this many pennies. Okay, this special number here, this 6.02 times 10 to the 23, is what we call Avogadro's constant. And you may be thinking, why on earth is 1 mole this many things? It's a ludicrous number. But we will explain that point very, very shortly. The important thing for now is that we understand 1 mole of anything is Avogadro's number, 6.02 times 10 to the 23 of that thing. In this case, that thing is pennies, which is absolutely fine. And just for the fun of it, let's work out how many Great British pounds that would be. So there's 100 pennies in a pound. 100 is 10 squared. So if I wanted to divide this by 100, I divide by 10 squared, and I simply need to reduce the power on my 10 by 2, and so I would have this many Great British pounds. A very attractive prospect indeed. Next up, we can take a look at how many atoms of H in 1 mole of H2 molecules. So if I've got 1 mole of H2 molecules, I've got this many molecules of H2. And in every molecule of H2, there are 2 hydrogen atoms, and therefore I simply need to multiply this large Avogadro's number by 2 to get the number of atoms that are there. So if I do that in my calculator, I get 1.204 times 10 to the 24 atoms of H, or hydrogen. And so finally I thought we'd take a little look at this. How many atoms of oxygen are there in 3 moles of carbon dioxide? So once again, 3 moles. That means I've got 3 lots of Avogadro's number, so 3 times 6.02 times 10 to the 23 molecules of carbon dioxide. And in every molecule of carbon dioxide, I have 2 oxygen atoms. And so if I wanted the number of oxygen atoms present, I simply need to times this total by 2. And instead of having the molecules of carbon dioxide, I have the atoms of oxygen are present. Once again, if I put that in my calculator, I get 3.612 times 10 to the 24 atoms of oxygen. So you may already be starting to figure out why a mole is so important in chemistry. If I want to talk about amounts, I don't want to talk about amounts of atoms because they are insanely large. They're of the order of 10 to the 23, and it just wouldn't be practical to keep writing such big numbers. But a mole solves that problem. Okay, but why 6.02 times 10 to the 23? Well, let's see that now. So now I'm going to try and justify Avogadro's number, 6.02 times 10 to the 23 things in a mole. So what happened was we took carbon 12, and we knew that carbon 12 had a mass number of 12. In other words, it had 12 protons and neutrons being the only subparticles which have an appreciable mass. Electrons, remember, have a negligible mass. And we asked ourselves, how many atoms in 12 grams of this carbon 12? And the answer was this many, Avogadro's number. And so we said, well, let's call this quantity of atoms 1 mole. And as such, I know that 12 grams of carbon 12 has this many atoms, and therefore 12 grams of carbon 12, by the definition I've just constructed, is 1 mole. And this is incredibly convenient for chemists because now the mass number isn't just the total amount of protons and neutrons, but it is the grams per mole of that element. Indeed, carbon 12 weighs 12 grams per mole. And I could take a look at another element, for example oxygen. Oxygen has a mass number of 16, and therefore I can be certain that every mole of oxygen weighs 16 grams. Indeed, 16 grams per mole. Or for example, let me take krypton. Krypton has mass number 84, and therefore it weighs 84 grams for every mole. And so going forwards in chemistry, I would like everyone to remember that any mass number in the periodic table has units of grams per mole And it is this mass number, this relative atomic mass as we call it, that is going to allow us to convert from grams mass to moles amount, and indeed back the other way. And so I just very quickly want to discuss the standard units of mass. Technically, the standard unit of mass is kilograms. That means if you have an equation in physics and you use kilograms in that equation, you can expect your answer to also come out in standard units. For example, newtons, seconds, joules, etc., etc. However, because in the periodic table our relative atomic masses tend to be in grams per mole, it is true that grams is slightly more commonly used in chemistry. But technically you need to be reading the question and looking at the units to be certain. However, if you're in doubt, use grams in chemistry, use kilograms in physics, and if it's not a trick question, 99% of the time you're going to be correct. And there's one more common point of confusion that I'd like to take the opportunity to clear up. People often think mass and amount are the same thing, and that's simply not true. For example, if I asked you to buy 1,000 kilograms of sunbeds and 1,000 kilograms of chairs, we would not have the same amount of sunbeds and chairs, because sunbeds weigh more than chairs. And therefore clearly mass and amount are not exactly the same thing. And it's the periodic table with all of its relative atomic masses and its grams per mole that is going to allow us to transform from masses, grams, to moles, amounts, and that's exactly what we are going to see right now. And so now I'd like to take a look at all of the different quantities in chemistry that can be converted into moles, i.e. into an amount. So first of all, we have mass, and we've already started to touch on this because we have seen that in the periodic table, these numbers up here, the relative atomic mass numbers, are given in units of grams per mole, and therefore by that logic, my relative atomic mass, I'm writing M here for relative molecular mass to keep it more general, is equal to grams, so mass in grams per mole. And so I can simply rearrange this equation to make moles the subject if ever I need to go from mass in grams to moles. And now next up I have concentration. Concentration is typically given in units of moles per decimeter cubed. So let's quickly recap what a decimeter cubed is. Here I have a cube that is 1 decimeter by 1 decimeter by 1 decimeter. In other words, it's a 1 decimeter cubed cube. And a decimeter is 10 centimeters. So this is the same as 10 centimeters by 10 centimeters by 10 centimeters. And therefore this 1 decimeter cubed must simply be 10 by 10 by 10. In other words, 1,000 centimeters cubed. Okay, so we have established that decimeters cubed is a unit of volume, and therefore concentration, which is moles per decimeter cubed, must simply be moles over volume, where that volume is typically measured in decimeters cubed. However, if it were measured in centimeters cubed, no issue. We've just discovered that 1,000 centimeters cubed is 1 decimeters cubed. So if need be, we can convert between centimeters cubed and decimeter cubed. And as such, I can use this equation once again, making moles my subject to go from concentration to moles. And so last but not least, that brings us on to volume of gas. So if we think about gases for a second, whether the particles are big molecules or small atoms, the particles are always tiny relative to the room that they find themselves in. And therefore the volume that they occupy should really only depend on temperature, pressure, and of course the number, the amount of gas particles that are present in that volume. And that's what we're going to see now. And so on the board I have written a fact, which is that at room temperature and pressure, room temperature being about 20 degrees Celsius and room pressure being about 1 atmosphere, which is 10 to the 5 pascals, 1 mole of gas, and it can be any gas, will always occupy the same volume, and that volume will be 24 decimeters cubed. Now if you're an IB student, you may have learned this with standard temperature and pressure. Standard temperature is just a little bit lower, it's 0 degrees Celsius, and therefore the volume of gas occupied will actually be 22.4 decimeters cubed. Regardless, the important point here is that this allows us to convert from volume of gas, decimeters cubed, into moles. Indeed, if every mole occupies 24 decimeters cubed, then I only need to see how many times does 24 fit into my volume of gases, volume divided by 24, to work out my amount in moles. And hence I can comfortably go from volume of gas to moles. And so we shouldn't forget the one other way we could be asked to find the moles of something is from a balanced chemical equation. And in this case, normally what happens is we know the moles of one chemical, we use the balanced chemical equation and the molar ratio to find the moles of another chemical, thereby going from moles to moles. Let's take a look at that now. Now, just a few notes before we go and balance this equation on the board here. When I balance an equation, I can only stick big numbers in front of my molecules. I can't stick in little numbers, like for example here, a 2, because that actually changes the chemistry. It's no longer carbon monoxide, now it's suddenly carbon dioxide. So little numbers, not okay, but big numbers I can stick them in wherever I wish, and indeed I should, such that I have the same total amount of each atom on both sides of the equation. Now there are methods which always work here, however they can be quite complicated to learn, and I normally find that simply inspection suffices. What do I mean by inspection? A little bit of trial and error and a little bit of common sense. For example, if I look at this equation here, I notice that Fe is simply by itself, so if I stick a big number in front of Fe, it's not going to change any other elements in this equation. So I'm going to leave Fe to the end because it's easy to balance. Maybe I pick a more complicated one like an O, and I see here there are 4 O's on the left hand side and 2 O's over here. So I have a go and I say let's put 2 here, such that there's 4 O's here and there's a total of 4 O's here. Looks like a good start. And I notice now there's 2 carbons and 1 carbon here, so let me stick a 2 here. Aha, but the issue is this has now changed my number of O's again. And I take a step back and I say, well, now there are a total of 5 O's on the left hand side and 4 O's on the right hand side, and I notice that on the right hand side I must always have an even amount of oxygens because they're always coming in pairs. So I know straight away this 2 can't work here because this would give me an odd number of oxygens because I have an odd number here plus an even number here. And so that suggests to me that perhaps I should use a 3 here, and if I use 3 here, I should use 3 here, and now I can see that my carbon and oxygens are balanced, right? 3 carbons, 6 oxygens, and 6 oxygens. And so finally, as agreed, I just need to balance my Fe, but that is a piece of cake because I can stick any number I want in front of here. It's not going to affect the carbons and oxygens, and the number I want to stick in front of it is a big fat 2. So there we go. And so now we need to cover exactly what these big numbers represent. They represent the ratio of the amounts of each substance in this equation. An amount is just moles, therefore it's the molar ratio. So I have 1 mole of iron oxide for every 3 moles of carbon monoxide I have, for every 2 moles of iron, and for every 3 moles of carbon dioxide. This is my molar ratio. And so now we can have a go at answering this question here, which asks, if I have 12 moles of carbon monoxide and my iron oxide is in excess, what does that mean? It means there's more than enough iron oxide. Iron oxide is not going to be the thing that controls how much product I get because there is ample supply of it. How many moles of iron should I theoretically expect to produce? Why theoretically? Because of course in experiments things go wrong, we might lose some iron, there might not be a complete reaction. When I talk about theoretically producing this much iron, I'm talking about in a perfect scenario, i.e. from the quantitative chemistry analysis. Okay, so I've got 12 moles of carbon monoxide, so let me write 12 down here, and let me check out my molar ratio between carbon monoxide and iron. It is simply 3 to 2, and so I must very simply write the ratio of 3 to 2 as 12 to 8. And therefore, there would be 8 moles of iron theoretically produced. Okay, so that's all the theory, but stay with me because now we're going to put it into practice with some examples. So first of all, I'd like everybody to read the question, perhaps have a go at it themselves, and therefore I'd like us all to pause the video in 3, 2, 1, now. Okay, so let's have a little look at the solution to question A. I've been asked to work out which reagent is in excess out of sodium carbonate and nitric acid. And it's very tempting to look at this and say, well, hang on a second, there's 0.1 moles of each. Surely that means there's the same amount of each and neither is in excess. But we have to be careful. Yes, there's the same amount of each, but should there have been the same amount in light of the balanced chemical equation? And the molar ratio here says there should be 1 sodium carbonate for every 2 nitric acids. So what I like to do here is I like to say what would happen in an ideal world. In an ideal world, if I had 0.1 mole of sodium carbonate, then I would require twice as much nitric acid, and I should have 0.2 moles of nitric acid. I then look at this and ask myself, do I have that? No, I have significantly less, and therefore this is the limiting reagent, and this is in excess. So think of it as a sort of thought process. You say to yourself, in an ideal world, I would need how much nitric acid with this? I would need twice as much, 0.2 moles. I don't have that much, therefore this is the limiting reactant, and therefore the other chemical, which is sodium carbonate, is in excess. Okay, and so this is really important for the second part of this question, which is finding the volume of CO2 produced at room temperature and pressure. The reason that it's important is it is the limiting reagent or limiting reactant, the terms are synonymous, that controls how much product is produced. Okay, so if I refer back to my mole diagram, I can see over here that this is now going to be the case of mole to mole, right? I have a balanced chemical equation, and I know that I have 0.1 mole of nitric acid, and I would like to find how much carbon dioxide is going to be produced. The ratio is 2 to 1 for nitric acid to carbon dioxide, and therefore if there is 0.1 mole of nitric acid, there must be 0.05, i.e. half of that quantity, moles of CO2. And then finally, I can look back at my mole diagram again. I can say I've got my moles of CO2. I would like to go to volume of gas, so I need to use this equation here, and I can very simply say 0.05 moles times 24 decimeters cubed per mole. Remember, that is the amount of volume any mole of gas occupies. We discussed that earlier, and that gives me 1.2 decimeters cubed. I could have used the fact that they said in the question that any mole of gas occupies 24,000 centimeters cubed. It would give me completely the same answer. I would just have my answer in centimeters cubed, which would be 1.2 times 1,000, 1,200 centimeters cubed. In this question, they didn't specify which unit they wanted the final answer in, so both of these are. Okay, so I've cleared the board, and now we'll take a look at question B. Well, question B is very similar to question A. The only difference is, yes, here I am given a molar amount of nitric acid, but over here I am not given the amount in moles of sodium carbonate. So first of all, I must use this branch of my mole diagram to convert from concentration to moles. No problems at all. Let's take a look at the units here. This is in centimeters cubed, this is in moles per decimeters cubed, so I need to put this into decimeters cubed. Remember, the conversion factor is 1,000, so 20 divided by 1,000 gives me 0.02 decimeters cubed. And so my equation is moles equals concentration times volume. And that makes perfect sense in terms of my units, because my concentration is moles per decimeter cubed, my volume is in decimeters cubed. These would cancel and I would be left with moles. So there's no doubt in my mind that this is the correct equation. Let me fill in the numbers. The concentration, it says up here, is 0.1. The volume we just worked out is 0.02. Times those together and I get 0.002 moles of sodium carbonate. And so now I can shrink that down and compare that with the amount of moles that I have for nitric acid. So I have 0.02 moles of nitric acid. We can apply the same method that we applied last time. In an ideal world, 0.002 mole of sodium carbonate should be reacting with twice as much nitric acid, i.e. 0.004 mole of nitric acid. We can quite clearly see here there is a lot more than 0.004 moles of it, and therefore this is in excess, and this was my limiting reagent. So I'm just going to get rid of this part down here to open up some space on the board, and just remember that the limiting reagent is 0.002 mole of nitric acid. That's going to be what controls how many moles of carbon dioxide I get. We can see that the ratio between nitric acid and carbon dioxide is 2 to 1, therefore I should have half as much carbon dioxide as I had nitric acid, means I have 0.001 mole of carbon dioxide, and I can quite easily convert that into a volume of gas as I did last time. This time I'll just use 24,000 centimeters cubed, so I have 0.001 moles. I have 24,000 centimeters cubed of volume for every mole, so times that by 24,000 centimeters cubed per mole, and that very simply gives me 24 centimeters cubed. Once again, I could write this in decimeters cubed. All I would need to do is divide by 1,000. And once again, both of these answers are correct because the question didn't request any specific units. Seeing as the last example didn't include anything to do with mass, I decided to include this example too. Let's do it the same as last time. Everybody pause the video, have a read through and have a go by themselves first, and then we will go through the solution. Pause the video in 3, 2, 1, now. Okay, so let's take a little look at the solution. Now, the question for part A is actually very similar to the last example. I want to find out which reagent or reactant is in excess. The issue I have here is, sure, this is given as moles, my hydrochloric acid. However, my calcium carbonate is given as a mass, and remember, mass is not an amount. So I need to convert this mass into moles. Well, they've conveniently given me the relative atomic masses of each of the elements in calcium carbonate. But if they hadn't, I could go to my periodic table and I could simply find calcium, relative atomic mass 40, oxygen 16, carbon, where did he go? 12. But they've given it to us, so let's use that. So I want to find the relative molecular mass, and I find that by simply adding up the atomic masses of each. So I have 1 calcium, so 40, plus 1 carbon, 12, plus 3 oxygen, so 3 times 16. And if I stick that in the calculator, that gives me 100 grams per mole. That is my relative molecular mass. And so, as ever, referring to my mole diagram, I can see that to go from mass to moles, I want to use this equation here, mR equals mass over moles. So let me copy that over. mR equals mass over moles. I would like to make moles the subject, so I simply have moles equals mass in grams, which is given as 1 gram, over my mR, which is grams per mole, so 100 grams per mole, and therefore I have 0.01 moles of calcium carbonate. And so now, as before, I can compare this amount of moles with my 0.015 moles of HCl, and I can say in an ideal world I should have a ratio of 1 to 2. So in an ideal world, these 0.01 moles of calcium carbonate should be reacting with 0.02 moles of HCl. However, I can see that I don't have that many moles of HCl, and therefore HCl is the limiting reactant and calcium carbonate is in excess. Okay, and so to answer part B, I need to find the mass of CO2 produced. Well, to be able to do that, I need to look at my limiting reactant once again, because it is that will control the amount of CO2 produced. So let me get rid of this, and just remember that my limiting reactant is 0.015 mole of HCl. Okay, so I've got my limiting reactant, 0.015 mole of HCl, and I know from the balanced equation that for every 2 moles of HCl, I should get 1 mole of CO2. So what am I doing on my mole diagram here? Once again, I'm going from mole back to mole using the balanced chemical equation. So I use this molar ratio, 2 to 1, therefore I must divide this by 2, 0.015 over 2, and that gives me 0.0075 mole of CO2. And so then finally I need to make this maneuver on my diagram. I need to go from mole all the way back to mass. So same equation again, I just need to use it rearranged in a different form. So the equation is mR equals mass over mole. This time I would like mass, so mass equals mole times mR. I will need to work out the mR of carbon dioxide, but that's fine. Carbon dioxide is going to be 1 carbon, which is 12, plus 2 oxygens, which is 2 times 16, and therefore I have my moles, 0.0075, times the total of this, which is 44, and finally I get that the mass of carbon dioxide produced, theoretically, is 0.33 grams. So there we have it, the mole. At first it might seem like it complicates and confuses chemistry, but actually it's designed to do the complete opposite. Let's just imagine water for a second. Water's relative molecular mass is 18 grams per mole, and therefore if I have 18 grams of water, I have 1 mole. That is far, far easier to talk about than 6 times 10 to the 23 atoms, which is this incredibly, unfathomably large number. And so praise be to the mole. And so there's nothing left for me to say other than get in that exam, whack-a-mole, and on behalf of JTC Education, see you online very soon.